Here's a relatively quick but an important one, talking about the concept of motional EMF and energy transfers. What does that mean? So imagine you have a loop of wire and a region of magnetic field. So here's the magnetic field going into the page, and here's a loop of wire where some of it is in the magnetic field and some of it is not. To make life easier, the magnetic field here is perpendicular exactly to the area. So if you recall, the definition of magnetic flux is the integral of the vector for magnetic field and the vector for area. Now, the magnetic field can vary. Here it doesn't, so it makes it much, much simpler. This is just going to be BA. So the magnetic flux is equal to BA in this example. Now, magnetic flux, I like to tell my students, if you've watched more than one of these videos, you've heard that you can vary the magnetic flux in one of three ways. You can vary the strength of the magnetic field. That's not changing here. You can vary the orientation of the area vector relative to the magnetic field. That's not happening here either. The magnetic field vectors are perpendicular to the surface. They're piercing it. And the vector representing the area is parallel to the direction of the magnetic field. So you don't have to worry about the dot product. So what we have here is BA, and the area is changing. Now, not the area of the whole loop, but the area that is in the magnetic field is changing. Why do we care? Because Faraday's law tells us that there'll be an induced voltage that is equal to the change in the magnetic field flux, or the magnetic flux, with respect to time. So in this particular case, B is not changing, so I can pull that out. That is just a constant. Now the area is changing. In fact, I'm going to not write the negative sign here. That may bother people. B, now A dt. Now if you look at A, this L is not changing. However, the area is changing in this direction. In fact, that rate of change is dx dt. So this sort of becomes E equals B L, and then the width is changing at a rate of dx dt, but we have a better name for dx dt. That's velocity. So E equals B L V, and I watched a video not too long ago from a teacher I recommend to my students highly, the Lasse Viren 1, and he dropped a line about E equals believe, so I'm stealing it. So E equals believe. Now, why did I cross off the negative sign? It's not that it's not there. The negative is just to remind us that it's going to oppose any change in flux. So what direction is the current in the green loop here? Well, the magnetic field is going into the page. So the induced magnetic field is going to oppose that change. So less into the page is the same as more out of the page. So if you're pulling it this way, and this is the direction that you're applying a force, the change in the flux is less into or more out of the page. So what we need is our induced magnetic field to oppose that. So if it's coming more out of the page, we actually want to have an induced magnetic field that is going into the page as well. So to make that happen by a right-hand rule, we're going to have current going around clockwise. Now to get the magnitude of that current, you're just going to take, Ohm's law. I is going to be E over R. Is going to be B LV over R. Now, you can look at some other interesting questions like, well, what's the rate of power that the circuit is consuming? Well, power equals I squared R, which is going to be B squared L squared V squared over R squared times R, or the electrical power used in this circuit is going to be B squared L squared V squared over R. Now, where's that energy coming from? It's coming from you pulling. So assuming you're pulling at a constant speed, you're pulling it to the right. There's also going to be a magnetic force. Let's see, what's a good color to use? How about purple? That's going to be equal and pulling it to the left. The reason there's a force on this part right here that's going down, if you use your right-hand rule and use your current going around clockwise, IL cross B is going to give you a force pointing to the left. And you may say, well, what about here? Well, there the direction of the current causes a force upward, but down here it causes a force downward. So those two, the up and down forces, cancel out. So what if we wanted to, for example, compute the force? Well, you can think about it two ways, either in terms of the force you're applying or in terms of the magnetic force. So from the magnetic force, you might say, well, magnetic force equals IL cross B. Great. This is I. And the I we have seen just a second ago is believe over R times L here from the L cross B times B, and you're left with a magnetic force is equal to B L squared V over R. Now, one of the things I love about physics is, things balance. There's checks. You can look at it different ways. So what if I wanted to look at how much energy the person is expending pulling this? So what force are they applying? And one definition of power, one that doesn't get used as often, is force times velocity. So if you want to know the force, you can actually take the power divided by the velocity. Well, we just figured out that the power was B squared L squared V squared over R. And then we're going to divide that by V. One of the V's cancels out, and lo and behold, you get exactly the same magnitude force. B squared L squared V over R. Look, these are the same thing. That's kind of exciting. All right, that's probably enough videos for today. I hope this one was coherent. And to my students, see you soon.